Yeah, what we need to talk about, we've been talking about these definite integrals. We need to talk about the indefinite integrals. Yeah. Yeah, the indefinite side of things. So called because here's what an indefinite integral looks like. An indefinite integral looks like this. Looks just like a definite integral, except no limits, right? There's no a to b. That's why it's called indefinite, because you're just doing it kind of in general for different reasons. Yeah, we'll need to talk about that. So, yeah, that's the only thing. It's just an integral with no limits. No limits of integration. Well, what that winds up being then is we're still going to do it the same way. We're just not going to have to evaluate it at the limits. For example, if I do the indefinite integral of x squared dx, I don't have any limits, so I just do the antiderivative, right? The antiderivative is 1/3 x cubed. One catch, though, because I'm not evaluating it, you know, this minus this, guess what I have to put in? I have to do the plus c. Yeah. I can get away without doing it on the definite integrals because, like we said last time, if on the definite integrals, you know, if you're talking 0 to 2 x squared dx, even if we put it in there, if we put the plus c in there, when we go 1/3 times 8 plus c minus 1/3 times 0 cubed plus c minus, the c's go away because you got a plus c and you got a minus c. So you don't have to put them in there. When you don't have those limits, you got to put them in there. Okay? Because, well, I mean, it's the same thing, but in a slightly different context, I guess, if you will. We're finding the function, you know, the antiderivative, basically. So we're trying to find all the functions that this could be true about, and that plus c has to be in there, because c could be 1, could be 1,000, 500, we don't know. On the definite side, it doesn't matter, but when you're doing it indefinite, yeah, you need the plus c. Okay, that's the really big change. The only slight change, anyway. Yeah, one thing that these are used for are tables of integrals. On tables of integrals, you'll see these indefinite integrals. You won't see, of course, definite integrals because it's a table. You're just showing the integrals in general. You know, one of them's on what page 3 in our book, 325, section. But yeah, they're using tables. The back of the book, you'll see tables of integrals. That's one use of the indefinite integral. Which is the one in this section. Yeah, we have the table of the trig functions, the integral of sine of x dx. Well, that's, you know, it's really just a table of antiderivatives, right? That's what it is. Negative cosine of x plus c would be the indefinite integral of sine of x. Cosine of x dx would just be sine of x plus c. Secant squared, that's another nice one, right? Because secant squared, you got the tangent plus c. Cosecant squared would be another nice one. It's negative the cotangent of x. And then the other ones are, you know, the ones you can do the integrals of nicely are the ones that are the nice ones. The antiderivatives are the ones that have the nice derivatives. You know, the derivative of secant is secant tangent. right? So the integral of secant tangent is secant. I think we mentioned that one before. So yeah, if you see secant x, tangent x in your integral, that's actually a nice integral.
So any constant is just a formality.
Huh?
So any constant is just a formality.
Well, on the indefinite, you just don't know. You know, we're really what we're saying is this gives us this function, and this function could be plus c, plus 100, plus 1,000. We don't know. You know, what we did in the last section of the last chapter was we said, here's a value at x is 2, the y value is 3. Then you can find c. So you can definitely find out what c is. So without knowing any more information, yeah, it needs to be in there. It could be 0. This is antiderivative, yes. This is just, we're just doing the antiderivative. We just now have another new notation for it. Yeah, so secant x, tangent x is a nice one. Cosecant, cotangent is a nice one, isn't it? Since the derivative of cosecant is negative cosecant cotangent, what would the integral of cosecant cotangent be? Well, it would be the negative cosecant. All right. Okay, so that's one use of it. Let me talk about just go through a couple of problems here. So really, this is nothing new. Actually, these problems are easier because you don't have to evaluate with the limits. So what would this one be? The integral theta minus 12 sine theta d theta. Well, the variable there is theta. That's just like x, isn't it? X to the first power. This is theta to the first power. So that would be 1/2 theta squared. Minus 12 sine theta, well, you got to think about, the integral of sine is negative cosine, so that make it a positive 12 cosine. Everybody with me on that? Plus c. Yeah. So the trade-off, you don't have to evaluate at the limits, but you got to remember to put the plus c. That's the trade-off. Okay? Which is what we learned. That's what we learned for antiderivatives anyway. We just didn't need it for the definite, but back to the indefinite you do. Okay? We talked about this one a little bit. What would I do here? Integral of x squared times x cubed. I'll tell you what. Let me change that. Let's say it's x squared plus 1 times x cubed minus 27 dx. What would I do there? Full it out first, yeah. Whenever we have a product, if you can multiply those together, that's what you want to do, because we said earlier the antiderivative of this plus times the antiderivative of that just doesn't work. So if you've got something that can be multiplied out for your integral. So yeah, FOIL that out, multiply everything out. X squared times x cubed is x to the 5th. X squared times minus 27 is minus 27x squared. 1 times x cubed is plus x cubed minus 27. Then it's just straightforward power rule antiderivative. 1/6 x to the 6th minus 27 over 3 be 9x cubed. 1/4 x to the 4th minus 27x plus c. What about this one? Integral x squared plus 4x minus 3 over x cubed. Same thing goes for divide. If you can actually divide this out, usually that's a good way to go. Go ahead and divide this out. In other words, divide this by x cubed. Wait, x to the fourth. I'm sorry. Change that to x to the fourth. I saw a problem as I was saying that. Yeah, change that to x to the fourth. Because we haven't talked about what we'd get if we had that x cubed. But anyway, yeah, if you can divide it out, that's probably the way to go. In other words, go ahead and divide by x to the fourth. Some people say change that to x to the minus 4 and then distribute it. Whatever you want to do. Just divide those separately all by x to the fourth. So you get x to the minus 2 here, 4x to the minus 3 here, and then minus 3x to the minus 4 here. Now it's just the power rules, antiderivative power rule. Add 1 and divide by that power. So what would that be? 1 over negative 1 x to the minus 1. This will be 4 over negative 2 x to the minus 2, minus 3 over minus 3 x to the minus 3 plus c. So yeah, all simplified out be minus x to the minus 1, minus 2 x to the minus 2, plus 1 x to the minus 3 plus c. Or if you want to, flip those over, make them positive exponents. You don't have to, but if you want to, you could. It's all the same. Either this or this, I would be happy with. It's not a power rule. Remember, we talked about it. If you have integral of x to the minus 1 dx, the reason you can't use power rules is because, yeah, you get x to 0, but what do you get here? 1 over 0, which is undefined. So that doesn't work. I mean, you can look it up in the table. It turns out to be the natural log of the absolute value of x. But for ours, in our courses, we do it. That's like the first thing we do in Calc 2. So. Yeah, the power rule only works for everything except for x to the negative 1.